All right, here we go. We've got lesson 3.1.2, rotations and translations. So these are new transformations. Our first transformation is called a reflection, and now we've got rotations and translations. Before we get to that, I want you to go to the methods and meanings section in your textbook. If you don't have it open, you can kind of look at this page. We are going to be referring to different polygons and things like that. So I wanted to cover this really quick. So a polygon is just a two-dimensional figure that's made up of line segments. So here I've got a whole bunch of different polygons made up of line segments. So they can't be made of curves. Each point of the polygon, each little point at the end is called a vertex. If a polygon is regular polygons means that all the sides are the same and all the angles are the same. So here we've got, this one is a regular polygon right there because all of the sides are the same. In this case, there's 6 sides, so we'd call that a hexagon. All right, so we've got some naming conventions on our polygons. For sides 3 through 10, we actually use their names. After that, we stop using their names just because it's hard to remember them all. So our first polygon is a triangle, a quadrilateral, pentagon for 5 sides, hexagon for 6 sides, heptagon for 7 sides. Some people even call this a septicon instead, but heptagon is usually the name we use. Octagon has 8, nonagon has 9, decagon has 10. Once we get to 11, we just start calling them 11gon. If it had 12 sides, we call it a 12gon, 13gon, 14gon. And it doesn't mean that they don't have names. It's just at that point, we stop really remembering their names. An 11gon is actually called I think a hendecagon, but we just don't call that anymore. So we're just going to start calling it anything bigger than 10. We'll just call the number and then the word gon after that. So sometimes we can classify the polygons with specialized names. Like in triangles, we've got right triangles, we've got acute triangles, we've got isosceles triangles. In quadrilaterals, sometimes we've got shapes that are squares, rectangles, trapezoids. So we can get, even within these polygon names, some of them have specialized names inside of them. But so really knowing these names is kind of probably going to be important at some point. So you're going to definitely want to refer to that as we start talking about polygons. So polygons, again, they're just made with line segments. All right, let's get to our actual lesson. All right, so get out your resource page for this one. Like I said, we're going to be going over rotations and translations, which are our other 2 transformations. So on our first problem, 3-14, we're going to start right here, 3-14. What we're going to do is we're going to take triangle ABC, and we're going to reflect it 2 different times. So we're going to reflect it over N, and then we'll have A prime, B prime, C prime. And then we'll reflect that image over P, and then that will be A prime prime, C prime prime, A prime prime, B prime prime, C prime prime. So each time that you reflect a reflection, you add another prime to it. Okay, so let's go ahead and reflect it first. Let's do it in red. So I'm going to reflect, remember, we just stay the same distance away. So this is 1, 2, 3 away. So we go 1, 2, 3 here. So there would be B prime, C prime. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So it's 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's C prime. And then A prime is I think right there. All right, so let's go ahead and fill in those lines. And what you have here is a reflection. We can tell it's a reflection because the facing of the triangle is different. So they're not facing the same direction. So there we got the original, the pre-image, and here we've got the image, and it's A prime, B prime, C prime, and it's facing in a different direction. So now what we're going to do is reflect A prime, B prime, C prime over line P. I'm going to go ahead and pause and let you do that and see where we end up. Okay, 3, 2, 1, pause. All right, so as we can see here, we had the reflection first, and then we reflected the reflection. And what we notice is that A, B, and C are facing the same direction that A prime prime, B prime prime, and C prime prime are. Oh, I wrote the letters wrong. This was supposed to be C. And this was supposed to be B. All right, sorry. So we can see that these ones are facing the same direction. Okay, so what we call that actually is a translation. So if we have where we're taking a shape and we're just sliding it around, so like this ice cream cone, we just slide it over here, and if it's facing the same direction, so its orientation, if its orientation is the same, then we call that a translation. So we notice that with a reflection down here, the orientation is not the same. It's facing in a different direction. So A prime, or ABC to A prime, B prime, C prime, so this one to this one, that we call a reflection. But if we take a reflection and reflect it again, this one to this one, so ABC to A prime prime, B prime prime, C prime prime, if we do that, then the orientation doesn't change, and that's called instead a translation. All right. So a translation is when the orientation doesn't change. So we've just taken it, it's like we put our finger on it and slid it somewhere else. All right, 3-15. All right, this first part is going to be done on the resource page, so hopefully you still have that out. So we're going to do our reflecting again. We're going to reflect over line V, so it's going to be in a different orientation, so it'll be a reflection. And then we're going to reflect over this diagonal line, which is going to create what we're going to call a rotation in a second. So let's go ahead and reflect here and then reflect here. I'm going to go ahead and pause, give you a chance to practice this, and then we'll come back. So pause in 3, 2, 1. All right, here's what we got. So our reflection looks pretty much like the last one did until we reflected over this line here. And then when we reflected over this line, remember you just kind of go diagonal to it to find out the spacing, and we get E prime prime, F prime prime, G prime prime. All right, so when we reflect over lines that are not parallel, we get what's called a rotation. So notice that this line here and this line here, they're not parallel, whereas in the previous problem, they were parallel lines. When they were parallel lines, we got a translation. When they're not parallel lines, we get something called a rotation instead. And what has happened is at point P, the paper, it's like it gets spun around. So here, now that I've spun it, you can see that this is the same orientation as the original EFG. So what happened to the image, or the pre-image, is it got rotated. It got spun around. So this is what a rotation looks like. So when we rotate, we have a center of our rotation, or some call it a point of rotation, and everything stays the same distance to that point as we move around it. So notice that the bottom of the cone is still the same distance from that point, and the top of the cone is the same distance from that point. So we're just keeping our distances to the point the same, whereas in a reflection, we were keeping the distance to a line. In a rotation, we're keeping the distance the same to a point instead. All right, so we can go clockwise or counterclockwise. If we go this direction, we would call this a clockwise rotation. If we go the other direction, we call that counterclockwise. And I'll just write CC, and that's usually how we write it, is counterclockwise. All right, so either one of those are reflections. Okay, so is it possible to rotate EFG counterclockwise to produce that? Okay, so I don't know if you've noticed, but this is a 90-degree rotation here. Now, how do I know it's 90 degrees? Well, for starters, this line here is a, a horizontal line. And then over here, it became a vertical line. Horizontal to vertical, spin your paper 90 degrees. Horizontal to vertical is a 90-degree angle. And then we can even see that EF is actually perpendicular here, so that's 90 degrees. So this has been 90 degrees in this direction. Now, 90 degrees in the clockwise direction is the same as what in the counterclockwise? So how many degrees counterclockwise would be equal to 90 degrees clockwise? The answer is 270. Oops, 270. I cannot write this morning. So 270 degrees counterclockwise is the same as 90 degrees clockwise. All right. So next one, part E, go back to your resource page. On this grid below, we're going to take this L and we're going to rotate it 90 degrees counterclockwise. Counterclockwise means we're going to go in this direction. Against the clock is what counterclockwise means. So we're going to go that direction. And Q, when it says about Q, that's going to be our point of rotation. So I'm going to put my pen down there and spin it. Let's just see what it looks like 90 degrees. So if I'm spinning at Q, 90 degrees, our shape should look like that. So kind of keep that in mind. Our shape should look like this when we're done. Okay, I'm going to spin it back to what it was supposed to be like before. Okay. So knowing that I'm going 90 degrees, that means this vertical line here, if I do 90 degrees about Q, should be a horizontal line instead. So this vertical line is 1, 2, 3, 4, 5, 6 units long. So I'm going to go 1, 2, 3, 4, 5, 6 units this way. I think I counted it correctly. We'll see. All right, so rotating it this way about this point, this line becomes this line here. And notice they're 90 degrees to each other because we're rotating it 90 degrees. Okay, so this horizontal line would become a vertical line right here. And this is 1, 2, 3, 4, so that's 4. So this vertical line would become 1, 2, 3, 4. Wow, that was really bad. This is why I use rulers. And then it would go 1, 2, 1, 2, and there's our new shape. We've rotated that L onto its side, 90 degrees. All right, 3-16. All right, so I've got a, put this away. I've got a transformation. Now remember, our transformations are rotations, reflections, and translations. The translation and transformation sounds a lot alike, but it's different. Remember, this one is the translation where it just moves. So these are types of transformations. What type of transformation is shown right here? Hard to tell because they're both squares, but look at the letters. Look at how the letters are, and then see if you can tell what kind of transformation that was. Pause and let you think of it. So the first thing that you should ask yourself, is the order of the letters any different? In this case, A, B, C, D, A, B, C, D. The order of the letters is not any different. So this one was translated from here to here. We just took it, put our finger on it, and moved it over. So this would be a translation. All right, now this one is going to be rotated 180 degrees. Okay, 180 degrees means 90 and then 90 again. Where would all of the letters be if we did that? So I want you to write A prime, B prime, C prime, and D prime over here after 180 degrees. Remember, that's two 90-degree turns. Where would all the letters be if we did that? I'm going to pause and let you write the letters. All right, so here we've got our order. So why does A prime show up way over here? Well, if I go 90 degrees, think about it. If I do 90 degrees, A prime would show up where B is. A second 90-degree turn makes A prime go to where C is. So that's why A is over here. B goes 90 and then 90 more, so that's why it's down here. C goes 90, then 90 more up here, and D goes 90, then 90 more goes to there. So 360 degrees gets you to where you started. So 90 degrees gives you one turn, 180, 270, and then 360 gets you to where you were at the beginning of it. All right, let's move on to 3-17. All right, now let's talk about the word rigid transformation, and this is a important word that we're going to do. A rigid transformation is a transformation where the shapes keep their side lengths and angles and angle measurements. So what that's saying is when we move a shape, what it's going to do is it's going to keep its side lengths and angle measurements, meaning that they're going to be the same size. They might be in a different order, or they might be facing a different direction, but the shape is still the exact same shape because you can measure out the sides and they're going to be exactly the same. Now here on part B, we've got two triangles and they're the exact same size. B to C is a distance of 2. B to A is a distance of 4. And over here we see this B to C is a distance of 2, B to A is a distance of 4. So they're the same exact size of triangle, but their shape is a little bit different. Not its shape, it's orientation. Sorry, that's the word. Orientation is slightly different. Okay, so can you describe a transformation or a series of transformations that can get you from this one to this one? Okay, we might have to do it in 2 steps. So think of our transformations that are rigid transformations. We've got our translation where we just slide it. We've got a reflection where we make a mirror image, and then we've got a rotation where we spin it. So is there a series of transformations that will get you from here to here? I'm going to go ahead and pause as you think about it. 3, 2, 1, pause. All right, so here's what I was thinking. I was thinking that I noticed that the order is backwards. So B, C, and A, and this is C, B, and A instead. So the order is a little bit different. So when the orders are different like that, I probably want to reflect it. So let's make a line of reflection. If I make a line of reflection right here, that line of reflection is the line x equals 3. Okay, so I'm going to start by reflect over x equals 3. Now when I do that, C would show up here. B is 1, 2, 3 away, so it's going to go 1, 2, 3 away here. And A would go 1, 2, 3 away, so 1, 2, 3 away. So here's my new shape, but it's not on top of the other shape. So I would need to do something else. What I could do at this point is I could start by translating down 1, 2 units. So if I translate down 2 units, all these points would come down 2 units, and then it would be on top. So I'm going to say then translate down 2 units. So that gets A, B, C over to A prime, B prime, C prime. So are there multiple ways to get that transformation, to achieve that? And you might have thought of different ways to do this, and that's fine, because there are multiple ways to do it. What if I would have reflected over the y-axis first? So flip this around. Then I could have moved back like 6 units and then down 2 units, and that would have worked for me as well. Or some people might have started this by moving it down 2 units and then reflecting over. And that would have given us the same exact transformation. So there's multiple transformations. Some people might have reflected over x equals 2 instead. And then if they did that, then they would have had to translate back and then down. So they would have had to translate to the right and then down to get it there. So there's multiple ways to achieve any transformation. Yes. And there's always going to be multiple ways to achieve a transformation. So there's going to be more than one right answer for most of these transformation questions because there's multiple ways to get there. It's just kind of what you are visualizing in your mind. And I'll teach you a little bit later how to double check what's going on by using slopes. All right, so 3-18. Would a series of rigid transformations, remember rigid transformations means that they keep their shapes, preserve the area of a polygon? So if I said I had a triangle, and this triangle had a side of 2 and a side of 5. So we know that using the area formula, that's area equals 1/2 2 times 5 equals 5. So if I did some kind of transformation with that, would it still have the same area? And the answer is yes, because the side lengths do not change. It will always have a side of 2 and a side of 5, so that will work. So when we do a transformation with a polygon, the area will stay the same. So we'll say yes, because the lengths do not change. Next one. If 2 polygons have the same area, are they always made from rigid transformations? Okay, we got 2 polygons, same area. Are they automatically the same rigid transformation? The answer is no. Let's see if you can come up with an example of why that would not be true. All right, think about that, and I'll show you my example in a second. So pause in 3, 2, 1. So here's my example. I've got a square that's 2 by 2, so that's got an area of 4. And I've got a triangle over here that also has an area of 4. They have the same area, but that does not mean that they're a rigid transformation. The shapes are different, so that can't be a rigid transformation. So therefore, you can have the same areas, but not be a rigid transformation. So this would be a no. Okay, and then the last part is just verify the shapes in 3-15. 3-15 was way over here. So verify that what we're saying is true, that we do have the same area. Let's just do 3-15E right here. Let's look at the area for both of those. Okay, so let's find the area of the original one. I'm going to split it up. So this section up here is 2 by 4. So that has a total area of 8 squares. And this bottom part has 2 by 4, so that's 8 squares. So that's a total of an area of 16 square units. Now let's look at this other one down here. So I'm going to split it up differently. This is 2 by 2, so this is 4 right here. And this is 2 by 1, 2, 3, 4, 5, 6. So 2 by 6 is 12. And we still get an area of 16 units squared. So even though we rotated it, the area of the shape keeps its area because the shape itself is keeping its side lengths. They're staying the same. All right, we've got our methods and meaning sections here. And that's the part on polygons that we already covered at the beginning. So that means we are all done. All right, enjoy yourself. Thank you very much. Bye-bye.